this video, we'll talk through the atomic orbitals topic from Advanced Higher Chemistry, Unit 1. By the end of this video, you should be able to describe the 4 quantum numbers and how these relate to atomic orbitals, describe the shapes of s, p, d, and f orbitals, and explain the Aufbau principle, Pauli exclusion principle, and Hund's rule of maximum multiplicity. Electrons within atoms have fixed quantities of energy, which are called quanta. It's possible to describe any electron in an atom using 4 quantum numbers. Our 4 quantum numbers are the principal quantum number, which is termed n. We have the angular momentum quantum number, which is designated L. We have the magnetic quantum number, which is ml. And we have the spin magnetic quantum number, which is termed ms. Our principal quantum number tells us which energy level the electron is found in. These levels are numbered from the nearest to the nucleus out to the furthest from the nucleus. Our first level would be n equals 1, second level n equals 2, and it would continue on. The higher the value of n, the higher the potential energy. Next, when we look at the angular momentum quantum number, the angular momentum quantum number determines the shape of the subshell, and it can have values from 0 to n minus 1. Each value of n is assigned a letter which indicates each subshell. If we have L equals 0, we have an S subshell. If L equals 1, we have a P subshell. L equals 2 is a D subshell. And if L equals 3, the subshell is F. In quite simple terms, this means that the first energy level has one type of subshell, which is an S subshell. The second energy level has 2 types of subshell, the S and the P. The third energy level has S, P, and D subshells, and our fourth energy level would have S, P, D, and F subshells. The magnetic quantum number distinguishes the orbitals available within a subshell. We have a range of minus L to plus L. If we're talking about S orbitals, L equals 0, therefore we've only got one value for our magnetic quantum number. In P orbitals, we've got 3 values for ml. Our d orbital, we have 5 values for ml, and for an f orbital, there are 7 values for our f orbital. In simple terms, this means that there's only one type of s orbital. We have 3 types of p orbitals, there are 5 types of d orbitals, and we have 7 types of f orbitals. Our s orbitals are spherical, and as the principal quantum number increases, the diameter of that orbital will increase. Each of our s orbitals can hold a maximum of 2 electrons. When it comes to our p orbitals, these have a dumbbell shape, and we have these lying across the different axes. Because we've got 3 potential magnetic quantum numbers, that means there's 3 types of p orbital. In total, this can hold 6 electrons, so 2 in each of these orbitals. Each of these orbitals has the same energy associated with it, and those can be termed as being degenerate. For our d orbitals, they have a more complex set of shapes, and we have got 5 different versions because we had 5 values for our magnetic quantum number. Got 5 orbitals, each containing 2, so these will hold a total of 10 electrons. When it comes to our f orbitals, these are more complex. There's 7 of them in each shell, which means they'll hold a maximum of 14 electrons. Our spin magnetic quantum number can either be plus a half or minus a half. If we have 2 electrons occupying the same atomic orbital, they must have opposite spins. So if one electron has a value of plus a half, the other one will have a value of minus a half. Here we've got a table that tries to sum up all of the different possible combinations, depending on if we're looking at a 1s versus a 3s orbital and looking at the various different quantum numbers associated with them. Some questions will give you a description of a quantum number and ask you to pick the correct term. This question we want to know about the one that determines the shape of an orbital. Shape means we're talking about s, p, d, or f orbitals, and this is determined by our angular momentum quantum number. We're now going to talk about the Aufbau principle. Pauli exclusion principle, and Hund's rule of maximum multiplicity. For Outbound principle, we have to be aware that all orbitals within a subshell will have equal energy. They are degenerate, and these orbitals are filled in order of increasing energy. This means we're going to fill the 1s before we fill the 2s orbital. You need to be able to write the order in which these orbitals will be filled, and one way of doing that would be to write out different possible options, and then using a diagonally sloping arrow, this shows us the order that we are going to fill them in. So we have 1s, 2s, 2p, 3s, 3p, and 4s, and then 3d. This is often written in order of principal quantum number. So despite the 4s orbital being lower in energy than the 3d, it's sometimes written just in terms of all the ones come first, then all the 2s, 3s, and then 4s. When it comes to our Pauli exclusion principle, we're going to focus in on the 1s orbital of helium. For these electrons, they have the same principal quantum number, the same angular momentum quantum number, and the same magnetic quantum number. But their spins will have to be different from one another. This means that we have got to have one electron spinning clockwise and one spinning anti-clockwise. So the arrows pointing in opposite directions is the correct answer. Our Pauli exclusion principle is summed up by the fact that no two electrons in an atom will have the same set of quantum numbers. The maximum number of electrons that we can have in any one orbital is 2, and these must have opposing spins. For Hutton's rule of maximum multiplicity, when we have degenerate orbitals, electrons are going to fill singly before pairing occurs. We are trying to maximize the number of parallel spins within our orbital. This means that our 3 electrons spinning in the same direction is correct. We'd only start to pair up electrons after each orbital has had 1 electron in it. Types questions that you can be asked, they can give you a particular rule, give you different potential explanations, and you have to pick the correct one. For Hund's rule, we are talking about maximum multiplicity. We are trying to get the maximum number of electrons spinning in the same direction. And looking at our answers, this means that A is going to be our correct answer. Another type of question, we can be given some information about particular atoms. In this question, we are given the ground state electron configurations for different elements. We've got our beryllium, nitrogen, oxygen, and our sodium. In the first question, we have to give the definition of the term degenerate, and degenerate means that the orbitals have equal energy. In the next part of the question, they're asking you to look at a particular electron arrangement and decide why this is incorrect. When we look at the 2p orbital, we can see that we've got 2 electrons in the first, and this has happened before we've got 1 in each of the boxes. Our orbital should be filled singly before any spin pairing takes place. This is breaking Hund's rule of maximum multiplicity. In another part, they give us the quantum numbers for the 1s electrons in beryllium, and they want you to state the 4 quantum numbers for the s electron in sodium. We have still got an s orbital, and the only thing that will be different is our principal number will change. This means we can have either 300 in positive a half, or 300 negative a half, or 300 half. Hopefully this video has helped you be able to describe the 4 quantum numbers and their relation to atomic orbitals, the shapes of s, p, d, and f orbitals, and what is meant by Aufbau's principle, Pauli exclusion principle, and Hund's rule of maximum multiplicity. Thank you for watching. Goodbye.